Hi, I'm Stefan, and I'm the organizer and host of the emBO++, the next level conference for embedded software developers. The talk you're about to see is by Matthew Venn. He explains how you can get from zero to your own ASIC with a completely open source toolchain. Thanks to Leica Geosystems, you can check out this talk online for free.
Thanks, Stefan, for inviting me. I'm going to try to keep this slightly relevant to emBO. It's more about learning how to design your own ASICs, but I think I've come from a firmware and hardware background, so I'm going to try and I'm going to kind of bring out the relevances. So talking a bit about that, kind of my last major job was CTO for this company that made this cool split keyboard that I've got on my desk in front of me. And that was kind of a bit of firmware, a bit of project management, a bit of circuit board design, that kind of stuff. I recently made an FPGA development board that is open hardware licensed. I've done fun things like building interactive robotic exhibits for science museums and DIY electronic music instruments. And I'm now Chief Sales Officer for Yosis HQ, and Yosis HQ makes open source FPGA tools and EDA tools. So kind of I'm fairly broad. And about a year ago, I got into the idea of open source ASIC tools because I felt like I didn't really understand what was happening at the lower level, and I got interested in that. So I started learning about it. And I want to compress a year's worth of learning into an hour's talk, which is going to be a bit of a push. And this is kind of my learning aims for you, anyone listening or watching the talk. So kind of a high level understanding why you might want to make an ASIC, see the tools in action on a simple design, get some familiarity with the jargon, and feel like it's an approachable thing, because I certainly didn't think it was approachable when I got started. I thought it was probably going to be impossible. And where to find help if you're interested and you want to learn more. So this is where I want to ask for audience participation. Really, it's an hour is nowhere near long enough, but it's okay. My voice won't last an hour anyway. But I've kind of got these topics in my talk, and I'd like to know where to focus. So could you raise your hands if you're interested in the kind of historical context of transistors and the road to where we are today? Okay, and raise your hands if you're interested in MOSFETs and the digital switches that form digital logic circuits. And raise your hand if you want to know how we turn all those tiny MOSFETs into a working chip. Okay, a bit more interest in that. There was a very exciting announcement last year of an open source process design kit, which is the kind of set of specifications from a silicon factory or a foundry from Skywater. And who's interested to know about that? Okay, cool. And then OpenLane is a set of open source ASIC tools, an ASIC tool flow that combines maybe 20 tools into a flow that lets you take a hardware description language file and turn it into the GDS2 files you need to send to the factory. Who's interested in that? Okay, and then who's interested in digital design with a hardware description language? And finally, who wants to know about Google's sponsored open source ASIC program where you can get free chips? Okay, that's really helpful. So what I'm going to do is I'm not going to skip over these first three sections entirely, but I'm going to go through them pretty rapidly and signpost you to resources if you're interested in more, and spend the majority of my time on these last four. So Why is this cool? Well, I see how open source tooling has kind of revolutionized my computing life over the last 25 years. I started using Linux about 25 years ago. Um, and I've always thought like this last step of like the actual silicon being open sourced is, how is that ever going to happen? And then last year was kind of the build up. There's FOSSI, the Foundation for Open Source Silicon, has been pushing for this for a while, but with the open source PDK and the tools and the sponsorship of the Shuttle last year, we're really starting to see this. And I think that it's going to make impacts in things like security, weird, unpredictable innovations that people aren't thinking about because the kind of big EDA tool vendors are so conservative and stuck in their ways. Simpler tools, greater accessibility. A typical license for the industry standard tools is about $100,000 a year. So it, as well as the great cost of making an ASIC, the tools for making ASICs is very expensive as well. And because the entrance fee, as it were, for the open source Shuttle is that your design has to be open source all the way down to the files you send to the factory, is resulted in this big growth of a library of open source IP that's been silicon proven. And I think that's going to be quite interesting in terms of making it quicker to build interesting things. One thing that I think is really fascinating about this topic is the huge range in numbers. So we're working with nanometers. So we've got kind of a meter and then a millimeter, and then 1,000 times smaller is a micrometer, and 1,000 times smaller than that is a nanometer. And nanometers is the kind of area that we're working on. And then on the other side of things, we've got 1.3 times 10 to the 22 MOSFETs made, the most manufactured thing ever made in history. It's quite incredible. I'm going to just skip past this, but recommend that this is quite a good book, old, but quite good. And one of the things that caught me about the book is that they're firm believers in learning by doing, which really fits me. And that's kind of how I've learned along my way to doing my first tape out. So first transistor, digital computers need switches. It started off being mechanisms, then electromechanisms like relays, then valves, transistors. And then we integrated lots of transistors. This is first IC when we put a lot of transistors together in 58. And then we see this rapid growth where we are today with millions or billions of transistors on a die. Here's a little video of a zoom in. So when you get a computer chip, it's like encased in a blob of epoxy. And if we erode the top of that off with some horrible nitric acid or something, we start to see the actual die, which is a lot smaller. So we have this big package to make it placeable by the machines that run on assembly lines, but the actual working element is much smaller than the package usually. And then we have these gold bond wires that come in from the outside to bond to the pad ring. I'm going to jump forwards now. We're going to move into the world of the electron microscope. And we start to see, here's the bond wires. These big tracks here are power distribution. And then as we get closer in, we see more these lines here. I'm just going to turn on this pointer. Oh, that didn't work. There we go. No, it's not on the video. These diagonal lines here, also power distribution. And now we can't just start to see the actual working structure. This top layer here is all the interconnects, like a PCB. And then underneath on the very bottom layer is where the transistors are. And these little blocks here are kind of Lego blocks that we can snap together to build up the digital structures that we need to make our computers. And at this level, we're starting to get to the final level. So in this particular technology, the width of the gate in the MOSFET is 1,000 nanometers. And the Skywater open source PDK, the width of the gate is 150 nanometers. So we're kind of 6 times smaller than this. And that's where we are with the open source PDK. Next slide, wrong way. There. So what are those little things that we see? They're called MOSFETs. They were invented by Mohammed Atallah and Dawan Kang in 1959. Metal oxide silicon field effect transistor. So it's a type of digital switch made in a specific way. And if you've ever done any kind of hobby robotics or electronics, that kind of stuff, you might have used one of these to turn on a motor. Here we've got a closer view. One thing I like about this is how, if you take a look at the circuit schematic, how it matches the cross-section of the actual device. And the way this works is, a simplified way of understanding it is, we've got a kind of a capacitor structure here. Whenever you have two parallel plates with some separation between them, you have a capacitor. So when we put some voltage on the gate, we charge up this capacitor, make it an electromagnetic field here. That changes the structure of this, of the property of this material here, which is a semiconductor, and it allows current to flow from the source to the drain, or the drain to the source, depending on how it's wired. You see, actually, this is a symmetrical structure. It's actually only made into a P, or it's only made into one or the other type of MOSFET by joining the body onto either this side or this side, and that defines which way the current's going to flow. But that's kind of a bit too in-depth for this talk. So why MOSFETs? They're easy to manufacture in volume. We can make really tiny ones for fast switching for digital computers, or we can make really big ones for turning on and off motors, that kind of thing. How do we use a MOSFET to make digital circuitry? Let's take the most simple element of a digital circuit, an inverter. This is their symbol, and we've got a truth table here: in 0, out 1, in 1, out 0. So here's our N-channel MOSFET. NMOS logic is all made entirely out of NMOS devices and resistors. So if we put a 0 in here, the MOSFET is off. So the pull-up resistor pulls the out on. So we get a high output that matches here. If we turn the MOSFET on by putting a high voltage in here, the MOSFET turns on and it drags this point down to ground. So this becomes 0 and we get a 0 output. So that's how the inverter works. And this kind of illustrates one of the problems, is that with NMOS logic, whenever we're in that state, we're always dropping current across this resistor and making a tiny bit of heat. So to get around that, people invented CMOS, complementary metal oxide semiconductors. So we're stacking acronyms on top of acronyms now. We add a new type of MOSFET, a kind of opposite MOSFET on the top. So that replaces the resistor. And that means that the device is much more efficient. So it's only using current when we switch between being on or off. We don't have that resistor in place all the time. So how do we actually make this stuff? We basically draw lots of little rectangles, and you could do that in any way you wanted. You could do it in Inkscape or Illustrator, or you could write a Python program that used a Python image library. The only thing you've got to do really is make sure you spit out at the end the right type of files for the Foundry, the GDS2 files. But they will reject them if they violate any of their design rules. So you need to make sure that what you're doing actually makes sense. But ultimately, you're just drawing patterns of squares in the right places on lots of different layers. And we've got about 30 different layers to draw on. So I wrote a little program and made the tiniest emBO logo. So this is 15 microns wide. And we could plonk that onto metal 5 of an ASIC chip, and you'd be able to see that under a microscope. But we would actually have some DRC issues with this. Like, for example, these tiny interior corners wouldn't be allowed. So we can make structures, but we can't. We can design the structures, but we maybe not necessarily be able to actually fabricate them depending on DRC rules, design rule check rules. So if you're interested to know actually how we take those designs and transmute them into physical structures on the silicon, then I'd really recommend watching this talk by Sam Zalouf, who did a talk for Hackaday SuperCon. And the super top level is you take a prepared wafer, you coat it in a layer of photoresist, you bake it, you take your mask of all these little rectangles that we've just designed in our emBO logo, put that here, shine ultraviolet light through it, which alters the photoresist. We develop it by washing it with a chemical, and now we've got a hole where all these letters are. Those are all holes. The rest is covered in photoresist. And then through those holes, we do something. We etch it away with acid to make a little hole. we bombard it with ions to change it into a P or an N-type MOSFET, we grow some metal layers there to grow a connecting wire. And then finally, we strip off the resist, and then we repeat that 30 times to build up a three-dimensional structure. So a three-dimensional structure might look like this. So this is a standard cell, which is like a standard block of logic that comes in the process design kit. And this is what the inverter looks like in the Skywater 130. So they're very three-dimensional. They're very thin and planar, but they're very three-dimensional in the way that they work. I really like the look of this. I think somebody should make a computer game out of this where you're kind of running around on the different levels. Here's a nice little cross-section. So at the bottom here, we've got our operational layer where the MOSFETs are. And then we've got 1, 2, 3, 4, 5, 6 metal layers that go on top. And you can see the way they're kind of arranged. Vertical, horizontal, vertical, horizontal, vertical, horizontal. And these things kind of patch together all the devices into the working structure that we're trying to build. So just to give you a little flavor of this, I'm going to show you how we could build an inverter using a ASIC design tool, a painting tool called Magic. So over here, I'll link to all these demos, and the slides will be shared at the end for anyone interested. So here's one I drew earlier. That was simple, wasn't it? So this is like my version of the inverter, and you can see this one is the N MOSFET. This is the P MOSFET. Here's the input, and here's the output, and then this connects to ground, and this connects to positive. And it's just like a painting program. So if I want to kind of redo something like this, I create a box, and I choose one of my 30 layers here. So I'll choose polysilicon for the gate. Draw a rectangle here for the P channel, P diffusion. Draw one here for the N diffusion. And now I've got 2 MOSFETs, and I can control them both with one gate. If I do something like this, and then connect this one to ground and this one to plus, join those together with another one, and this becomes my output. I can make an inverter like this. Now you see this kind of white highlight round here. This is telling me, Magic's telling me I've got 4 DRC rule violations here. As I've drawn, I've broken the rules from the foundry, and they wouldn't be able to make something like this. So you actually need to make sure that when you're designing, you're doing your work so that it fits within what is manufacturable. And a program like Magic loads the rules from the process design kit and shows you interactively. Now, Magic's a very old tool, but we still use it because it has a kind of superpower, and the superpower is being able to extract the circuit that we've drawn. So this circuit that I drew earlier, I'm going to extract the netlist and the parasitics. So what the parasitics are, for people who don't know, are unwanted side effects of the design that we've drawn. So when I mentioned earlier about having the gate of the MOSFET, you could understand that as a capacitor that we charge up. The capacitor is actually, we don't really want that capacitor because it takes a little moment of time to charge up and a little moment of time to charge down. So that limits the speed that we can turn on and off this, and that limits the speed of our processor or whatever it else is that we're designing. So Magic lets us extract those unwanted capacitances and resistances and inductances and everything else. And then we can simulate it and model it and work out how fast we think we can drive our designs. So I know this is going to be a little bit small in this window. So I'll just say what I'm typing in. I type in extract X2 Spice LVS. That sets up a bunch of things. X2 Spice C thresh 0. That says I want to extract the capacitance. And then X2 Spice again. And now that has dumped me out a file here called inverter.spice, where I've got a PFET model and an NFET model, and critically their width and length of the gate, which makes a big difference on how they behave. And then all these capacitances here. So again, if you've got any experience with building electrical stuff, you'll know that 0.006 femtofarads is extremely small, but these things all add up. If we had a clock tree that was driving 1,000 gates, we'd have to multiply that capacitance up by 1,000 times, and that slows down the edges of your clock, so it does become important. And I can run makesim, which runs a simulation with a program called ngSpice, and get some plots. So now I can see the input A is I'm generating that, it's going high and low, and then the output is the blue, and you can see that's following it. And what I can do here is zoom in and then measure it. And then down here, it's telling me it's taking 1 × 10⁻⁹ seconds for the output to follow the input. So that 1 nanosecond of time makes a difference. If I'm putting a lot of these gates together, tells me how fast I can run my clock while not violating digital design guidelines like flip-flop setup and hold times. And then here, this is, so I've done like, I don't know, 10, 15 years of firmware and microcontrollers, and a lot of stuff I do is power, like needs low power stuff. And I kind of understood, yeah, okay, saving power, you've got to do this, got to do that. But I never really realized that CMOS gates use this current when they're switching, only when they're switching, until I started looking into this. And this kind of really opened my mind to this, and it helped me understand why clock gating is used to save power with embedded stuff. You turn off a clock to a whole section of logic and it uses less power because the CMOS is only using power when it switches, and that's its great advantage over NMOS. So that was something new that I learned that kind of might be interesting to the embedded crowd. So let's jump back up to the slides and talk about the PDK. So we jumped through those first kind of 3 or 4 sections relatively quickly. What's my time at now? 5:20. So the PDK is Process Design Kit. And again, this is quite incredible that we have an open source PDK, because until last year, you would have to sign an NDA before you could use one. And what that means is it's very difficult for you to share with other people. So this is why we've seen, I don't know if you've been kind of seeing any of this stuff on Twitter, that's kind of my social network of choice. But at least in my timeline, there's been so much kind of open source silicon stuff in the last year. And one reason is because people are being able to share in a different way than before. We're seeing a lot more of the designs that people are actually making. So we don't have to sign a PDK. We can download this onto our computers and mess around with it and find bugs and fix them, because that's the cool thing about open source. And inside we get the DRC rules. We've seen them already in play with Magic. We've got the SPICE models that we can use to simulate the MOSFETs. We've got behavioral models for the digital cells. We've got standard cells for the digital design, which I'm going to talk about in a minute, and a whole bunch of other stuff. So in terms of what the digital standard cells are, they're like the big Lego set of all the logic blocks that you've got in your toolkit to build up whatever you want. So if you've done any FPGA stuff, you're always just using lookup tables to simulate logic cells like AND gates or OR gates. But with an ASIC, we can be much more efficient because we can just take the AND gate or take the OR gate. And we've got 5 or 6 different libraries here. And the one I'm most familiar with is the high density library. So that's optimized for maximum stuff in minimum area. But we also have libraries optimized for low power or high speed or high voltage. So let's take a quick tour of some standard cells. Presentation tools, make sure Sky or, oops, I need to do some kind of setup first. There we go. Okay, so let's take a look. Let's find an inverter first.
Wir sind hier in einem kleineren Grossraumbüro.
Bei der Leitung habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me, and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here and I don't have any issues living here.
Am meisten schätze ich in den Leica Geosystems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge my life hobby with my office job.
Das Besondere an der Leica Geosystem ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
So we can see that's quite similar to the one that I drew in Magic before. And they've got this very standard structure with this bottom, that's ground, and we've got this top bit, that's power. They kind of snap together into a grid. They are 3.2 microns tall. And if we zoom in on the gate, we've got 150 nanometers wide. So that's the width of the gate, as I mentioned in that video. Let's take a look at a 2-input NAND. Show his new top. So a little bit bigger. Now we've got 2 inputs, A and a B. We've got this output. What do you think is a 2-input NAND 8? Very similar structure. Why would we need something like that? Take a moment to have a glass of water. So the reason we want something like this is because it depends on how many other things we're driving. So if you think of like the clock in a microcontroller, it's got to drive thousands or tens of thousands of logic blocks, whereas like one signal that drives whether a GPIO should be an input or an output probably only needs to drive one gate. So if we've got a clock and we want to drive it hard, then we use something with big ganged out outputs. So all these MOSFETs, they're all connected together. 1, 2, 3, 4, 5, 6, 7, 8. And that makes an 8 times drive strength NAND gate. So we can use that to drive much more bigger trees of logic. And just one other thing that I think is quite interesting is, so memory is a completely different kettle of fish. And the reason why memory is so optimized is because this is the size of a flip-flop. So it's absolutely huge compared to an inverter. The inverter was about this wide, 1.2 microns, and this is on off the screen, it's so wide, 11 microns. So they're very inefficient in terms of space. So that's why we have DRAM, which is operating in a completely different way and is much more complicated, but much, much more optimized for area. And one of the cool things that I've been enjoying with not having signed an NDA to get the PDK is like when I've made my designs for various little bits and pieces, I can have fun playing with the colors, printing them out. And if I'd have been there in person at emBO, I would have been handing out these little ASIC GDS badges to everybody that wanted one. It's been super cool playing around with this kind of stuff. And I've got lots of artistic photos you can download for your desktop backdrops on this link. So here's a cross-section of the PDK that we have access to. And this bottom part here is where we build the transistors. And then we're using metal 1 for interconnects within the design. And then metal 2, 3, 4, and 5 to kind of make connections outside of that design. So it's a bit like having a 4-layer circuit board and millions of MOSFETs all in one package. So you can kind of see the power of that, but also how quickly things get really huge and unmanageable. So we've got 33 layers. The majority of them are for building the active components, the MOSFETs. And then we've got the metal layers for connecting things up. And then because of the package that Google has sponsored, we've got some layers that are related to that particular package. I'm going to get onto that later when we get into the shuttle. I'm just going to skip this over, I think. I will mention this. This is quite fun. Well, I thought it was fun, actually. This was my favorite DRC rule when I got started because this sounded the coolest. But as I've actually done my first tape out, I now hate it. So what an antenna rule is, basically, as you're building up MOSFET, you start off with the dopant to make it P or N type, and then an oxide layer and your polysilicon for the gate. And that is quite electrostatically sensitive. So then when you make big, long connections, and when I say long, I mean like a few microns across the chip to other things, they act as little antennas. And then in between this layering process, you have to flatten the wafer, and you're doing that by some form of etching usually. And that etching can put current on the wires, and if you're not careful, it can blow the gates. So an antenna rule is basically saying if a piece of wire is long enough and connected to a gate, it's got to either be grounded by a special ESD diode, basically, or it's got to be made shorter. And so when you're building and running the tools, you get these antenna reports that tell you if you've got problems with that and whether you need to add more diodes or make your traces shorter. So yeah, it's quite a cool rule, but it's actually ends up being really annoying because you end up with thousands of antenna rule violations. And it turns out it's important for yield. So you can just go ahead with it anyway, and out of 100 chips, only maybe 5 or 10 will die because gates have been blown. But if you're making millions or billions of chips, then you care about your yield. So you need to make sure you take care of antenna DRC violations. So what does 130 nanometers mean? We've got the Sky 130 nanometer. People talk about the node or the process. And it used to be that in the earlier days, the node was the same number of nanometers as the half pitch and the gate length. The gate length is this length here, and the half pitch is half the distance between the two metal layers. But technology has changed, and those numbers have kind of become uncoupled. And people are now saying the node has no meaning, absolutely no meaning, or the node is even nonsense. I read in a recent IEEE article, and people are saying you should have a different number because it's kind of just used as a marketing game now. It doesn't really mean anything. Now we've got kind of 14 or 7 nanometers, but it doesn't really relate to anything physical on the chip anymore. So it's kind of a marketing number. It roughly relates to density, but maybe you care more about memory density, or maybe you care more about logic density. So it's kind of, meaningless pretty much. 130 nanometers is fairly old. The process we're using comes from kind of the 80s or 90s, but it's still used a lot. So in Europractice ASIC service, 50% of the ASICs they make are 130 nanometers or bigger. So it's loved by analog people because it's very well characterized, it's cheap, and actually you can do a lot of stuff with the space, as we'll get onto in a minute. So on to OpenLane. So this is the open source tool flow that was released last year. You can download it and install it from here. I'm doing the demos with version 0.9. Takes about 15 or 20 minutes to set up, including the PDK. You need about 3 or 4 gigs of space on your disk to do it. The idea is you put in your hardware description language in the beginning, and then it flows all the way through, and out the end, we get the GDS2 files. And that's the files that we send to the foundry. And I'm going to kind of step through some of these steps in the process, as well as illustrating what is actually going on during that process. So to kind of get started with that, we need to know what our input files are, hardware description languages. So in reality, although you've seen how you can draw these structures to make ASICs, unless you're doing analog stuff, you're probably not doing much drawing. What you're actually doing is describing hardware with a hardware description language like Verilog, System Verilog, VHDL, or a higher level like Chisel or NMIGen or something like that. And this is how we can describe that same inverter that I drew using hardware description language. So assign output equals not input, wrap that up in some boilerplate, and that's an inverter. And then we've got kind of roughly two ways of dividing our way of describing circuits, either combinatorial, which is like big messes of logic gates all wired together. So an input changes and the output immediately changes. It takes some time to ripple through. So we could build adders or counters or things like that using combinatorial logic. And we also have sequential logic, which is usually clocked. So things only change on the clock. And we often have kind of combinations of this, some combinatorial logic that does some calculation, and then we clock it all into a register and use it sometime later. So in a CPU that you're probably all used to using as embedded engineers, we've got our registers, they're all made of flip-flops. We've got our ALU, and that's all mostly combinatorial logic. And then we've got a load of sequential logic for dealing with hashes and FIFOs and clocking instructions through the CPU. So with digital design, you're kind of breaking things down into smaller chunks. So this kind of simple design I'm going with today is a 7-segment second counter. So we have a 16 megahertz input clock, and on the output of our ASIC, we want to have a little 7-segment display that's counting up one every second. So extremely simple. Dedicated hardware, there's no software involved. This is just going to run forever without any firmware. So we've got an input clock at 16 megahertz. So we need some kind of divider to count that 16 million cycles and then make the output go high once. So we've got to have a counter here that counts up to 16 million. Then it triggers up the digit counter that increases by 1 every time until it gets to 9, rolls over back to 0. And then we have a decoder that decodes that number from 0 to 9 into the lights that we need to see on the 7-segment display. So this is what it looks like in Verilog. I'll take a closer look now. I need, to count up to 16 million, I need a 24-bit counter. So unlike C or something like that, where I'd say int or unsigned int second counter, I just say I want a 24-bit register, and then I only use 24 flip-flops, and I get exactly what I need. And then I say I want to count up to 10, so I need a 4-bit counter that can count up to 16, so I make a 4-bit counter. This is to do with simulating the design. So if I'm simulating it, I'm not going to count up to 16 million. I'm just going to count up to 100. And then I've got some sequential logic here that only happens on the clock. So I'm adding 1 to my second counter every time. So this creates a full adder, a 24-bit adder. So by writing this one line, the synthesis tool, Yosis, works out that I need a 24-bit adder and will synthesize the combinatorial logic to make that. And then here I've got a digit counter, and that uses a 4-bit full adder to be able to count up to 9 on the digits. So unlike on a CPU where you have an ALU and you can just reuse it, you have some firmware that is using the ALU over and over again. I've got in hardware now these 2 separate counters that are completely separate and parallel. And that is kind of one of the great advantages of doing stuff with a custom digital design, is because you can design the exact hardware you need for a specific task, and then it runs extremely reliably and with very accurate timing and with huge parallelism. So you could make that one counter, it takes up a certain amount of area, and then if you want 100 times the throughput, you just multiply that by 100 times, you've used 100 times in area, but now you're doing 100 additions every clock cycle. So that you can see that why people kind of spend so much time on custom graphics cards, because we're accelerating a specific thing that we need to have extremely parallel. Then down here, I'm doing a bit of modularity. I'm creating a new module called seg7, and this is the decoder, and this is all combinatorial. So as soon as the counter changes, the output segment changes, and this looks like a case statement, but actually gets evaluated as a big mux. Now what I can do is I can synthesize that, and I can simulate it. So I can do make sim, that's a rule in my make file. and then show this. And I can see that my clock is clocking, and my second counter is counting up. And because it's a simulation, it's only counting up to 100, and then it clocks over, and then the digit increases, and my output segments also change. So I can simulate this and kind of make sure that the design that I'm working on is doing the thing that I expect before I commit it to silicon. And I can also run this on an FPGA and get kind of some feedback that my design's going to work before committing to this kind of 2-month long process of sending out to a factory and waiting for my chip to get back that I realize I got the numbers out of order, which would be embarrassing. Yes, I'm still waiting on my first chip, so I don't know what embarrassing mistakes I've made, but the next time I talk, I'll be sure to let you know. Okay, so now I've got my little design here. I'm going to now drop that RTL into the top of open lane, and we're going to run it through open lane and follow the process and see what happens on the output. Still got time. It's cool. Okay, so we've seen this synthesis. I'd quite like to show you how it actually looks. I tried this earlier and it broke. So I'm just going to load up a design for a different design, just to give you the flavor of what it looks like. Mhm. So we take our HCl, which is nice and easy to understand, well, kind of easy, and then give it to Yosis, and then it synthesizes it into logic. So now we've got the logic that is available in our Skywater PDK library: ORs, inverters, NORs, buffers, inverters, on and on and on until we've built the thing that it is that we want. And this is actually a lot more complicated than that 7-segment display, but it's what I have to hand. This is an 8-bit divider. So you can see it uses up a fair amount of logic. But again, as before, now we have this and we can get a new result out of it every clock cycle. So we've got huge bandwidth capabilities here. So that's kind of, we've got our hardware description language, we synthesized it, we've got our digital netlist. And then the next part is floor and power planning. So I'm going to run the tools now. So they get done inside a Docker. So here I am inside the Docker, and I've got a configuration file, 7-segment seconds config, that's telling it what my desired clock period is going to be in nanoseconds, which is the clock port, where the Verilog files are. So I've just got that one Verilog file, how big a chip I want it to be, how hard I want it to work on making things dense or spread out. And then I can say flow design 7-segment seconds, and the tool starts up and starts running. And we start getting all of this log stuff out. And here we see output from Yosis describing what logic it needs. And then a bit later on, we can see how that gets mapped into the actual number of cells that we need. So to make that 7-second segments demo, we need 152 standard cells from the PDK, including 28 D-type flip-flops. So we needed 24 flip-flops for the 16 million counter. We needed 4 for the count up to 9 for the seconds counter. So 24 and 4 is 28. And then we've got OR gates and other OR gates and lots of different types of OR gates. Let's see how we're doing. And it's doing clock tree synthesis now, so we need to keep up. So it's done floor planning. So I'm going to switch to a different window here. Presentation tools, and I can say make Okay, layout, replace. Oh, that's first thing was, so this is another tool that I use to make it easier to do a presentation. So floor plan, there we go, K-layout floor plan. So it's just like shortcuts for these recipes that link to the specific intermediate files in the tool flow. So if I do make a layout floor plan, that's the first step. And it's we've got this 100 by 100 nanometer spot here with our inputs and our outputs. And we've got decoupling capacitors all down on the left side. And we've got these, here we go, what we've got here, decapping capacitors. And we've also got these things called taps, which make sure the MOSFETs are working correctly. So that's floor planning. And then we get placement, global and detail. So we get kind of rough placement and then detailed placement. So let's take a look at that. Replace. So here we start to see we've got all those cells we needed. So I can turn off the decoupling capacitors and the tap grounds. And we see these kind of cells all over the place. So we've got the cells that we saw that we needed, like those 28 flip-flops and all these OR gates, but they're all jumbled up. They're definitely not going to work like that. And then we do the finer routing placement. So now everything is lined up. So we see the value of this kind of modularity. We've got like ground and plus, and they're connected together with this power grid. So this kind of horizontal and vertical lines connect up with these vias here onto these horizontal lines. And then everything bonds onto that. So the cells are flipped one top or bottom depending on where they're matching up to. So we can connect them all up and get them nice and dense. So now everything is laid out kind of roughly ready for routing. And that's the next step. So now we're going to use metal layers 1 to 5 to make all these connections to join the logic cells up to do the thing that we want. Let's just see how the tools have got on. Okay, so the tools have, in that amount of time, the tools have finished. So it tells me somewhere how long it takes. Total time, 0. That's not correct, is it? Here we go, 2 minutes, 40 seconds. And we get a little report at the end of kind of problems and stuff like that. So, okay, so the routing is ready. So what's the next one? That's the final one. So make K-layout final. And so this is the final thing. I can turn on some other layers here. There's the missing. So we've got the clock port. So that's counting up the 16 million. And then we've got the LED segments out here. Again, I'm going to turn off the decoupling capacitors. They just kind of get in the way there. So now we can see how this is all laid out, and we can see the routing now. So we can see the routing. Oh, if I click on here, it tells me down at the bottom of the screen, that's on metal 1. So we can use metal 1 in between these power rails, but not crossing over them. So we use metal 2 going vertically to make these connections going over. So we can do most of this in just metal 1 and 2. And we would build up like blocks of macros and then be able to connect blocks of macros on the higher metal layers. So that's our finished design, and we've got the GDS file. So this GDS file that I've opened, that's the thing that we could send to the factory. So that's the whole open lane flow. And one other thing I want to show you is, let's quit out of that. Designs, 7 segment seconds. I get a different run directory for every time I run these tools. So I change into today's date. And then just, so there's 312 files made. So it can be a bit overwhelming to like know where the important ones are. That's why I've got this make file that just links the interesting stuff. And I just roll back up here. I've got a spreadsheet that's got a link here that's got the top most important files. So most of it is just kind of temporary stuff you don't need to care about. And then I've got them kind of ordered in most importance, what tool creates them, and a description and what they are. So the one we just looked at, for example, was this one, the GDS file. So that's the final thing we send to the factory. But also important are things like the LVS log that tells us if there's any problems being detected in the layout, or the antenna report. So that's the 7 segments full demo. And I'm going to jump ahead now to the shuttle. So just give me a minute to get some water. So about 10 minutes left. So I'll run through this last part on the shuttle, and then for people interested in asking questions, we can just go to a breakout room. I'll stay around for a while if anyone's interested in having a chat about this. So I started looking at this in March. Then we had this kind of announcement in June about the open source PDK, and the thing that really kind of got me on board was that Google was going to pay for me to tape out. So instead of me looking to raise 5 or 10 grand to have a go at this myself, now I got a chance to do it myself. And the idea is Google's sponsoring this for their reasons, and this is the philosophy that they're giving. I think there's lots of interesting reasons why this is happening, but one of the kind of most important things for me is they're paying for 6 shuttle runs, and on each of those 6 runs, there's 40 slots for your project. So if you want to get into this, you make a design. It's got to be open source. When the time opens, you make an application to eFabless, who's kind of working with the foundry. And then if you're lucky, you get in. So my design was accepted. My design's being taped out now, and I'm waiting to get the result back. And the next one's going to be in, they said it was going to be early 2021, but we had some delays. So it's more likely to be mid this year. So the next one's going to be mid this year. So it's not too late. Don't delay. Learn ASIC today. You can still tape out if you want to. So we made this tiny little 7-segment display, and that is fitted into 100 by 100 microns. And we've got 10 square millimeters. So not 10 by 10, because that'd be 100 square millimeters, but 10 square millimeters, more like 3 by 3. So we could fit about 8,000 of those 7-segment counters in the space that we've got to play with in the tape out. So there's a huge amount of space to experiment with. And part of the stuff that eFabless are doing to make it easier for us is giving us the pad ring. That's kind of the outside ring where the bond wires would connect to. And it's got a Pico RV32 RISC-V processor in there with some RAM and a Wishbone bus and some other bits and pieces like a serial port, GPIO. And you can build your project in there and then interrogate it with a built-in logic analyzer that you can control with firmware from the RISC-V processor. So this makes it, the pad ring is really easy because that's a lot of work that we don't have to do. And then actually having a RISC-V processor on board is also really useful because you can interact with your design. You can kind of make your design configurable and then configure it with a RISC-V processor. It's going to be packaged in wafer level chip scale package, which is admittedly quite small, but is doable for hand assembly. I've done a bit of BGA. It's not too bad, especially with an oven. And it's good for signal integrity. So there's some people doing radio stuff, and for radio stuff, it should be great. Although we're still kind of testing out the GPIOs, how they're going to respond to high frequency stuff. So in terms of fitting stuff on, I talked about the 7-segment display, but that's not really a great example because it's so tiny. So if we take the Pico RV32 processor, we could fit roughly 10 of those inside the project area. And here's some kind of other cores that have been synthesized, like a floating point multiplier. We could fit 10 of those in. IBEX core, fit about 8 of those in. An AES crypto core, fit about 8 of those in. So you can. There's a lot of space. This is what I did for my first tape out. I made a kind of a mux and put in 3 designs: that 7-segment display that I just showed you, a WS2812 intelligent LED driver, and a VGA clock. And then I teamed up with 5 other people who were up for having a go, but also had very small designs. So we tried to not waste so much space. So we put them all together. The firmware of the RISC-V CPU muxes them and chooses which one should run. In January, we got notified that there were DRC issues, and we had like these weird metal 5 layers that were shorting things out that were detected, luckily. And one of the people that was on the shuttle, who's coming from a much higher level up the stack of software programming, got really involved, made his own core, made his own application, and he was able to fix this issue. So I kind of put this in because even if you're not like super interested in doing your own ASIC, there's a lot of exciting software development work happening here, and people are making really great contributions. So Anton Blanchard fixed this issue in the tools, and now we don't have this weird Metal 5 issue anymore. This is an overview of all the designs. So this was my one, and then these other ones that I've highlighted in purple are ones done by people that I've interviewed to find out more about what they did. And you can see there's like such a huge variety of different stuff being done. We've had like radio, FPGAs, RISC-V cores, PowerPC cores, analog stuff, satellite, amateur radio satellites, all kinds of stuff. And it's going to be super exciting to see how this stuff works out. You can get more information on this link here. And one of the interesting things done was that 60% of the slots were taken by people who'd never done this before, so including me. This is some silicon that eFab has just got back recently. That is like a technology demonstrator. It shows the PDK has worked, that the IOs have worked, that the tools are working. And this is kind of like one of these exciting but very boring Blink demos. So very boring video, but exciting because the chip is one of the first open source ASICs done with open source tools on an open source PDK. So it's really like the start of something new. We're about here. We've done the MP1, MPW1, multi-project wafer 1. That's where everyone contributes their designs together into one wafer. MPW2 should be mid this year, and then there should be another one. And then Google have committed to 6, so there'll be 3 more. I'm working on a new harness with, instead of using a mux, I'm going to be tri-stating stuff to make things more compact and to fit more people's designs. So I'm trying to work on ways to waste less space and to get more people involved who want to try this but don't have big designs. And I've created a course in support of that called the 0 to ASIC course, which is like a 6-week asynchronous course where I support you on Discord and office hours, and you learn how to do this stuff on your own. Next course starting in April. It's all sold out, but I'm going to have tickets coming up in June. If you're interested, you can go to the website and sign up to the mailing list to know more about it. So that's it for my talk. These are all the people that have helped me along the way with learning all this stuff in my own 0 to ASIC journey in 1 year. And for more resources for you, go to the website. There's a newsletter, a list of terminology, interviews with lots of different people who've applied or people involved in the tools or the tooling, and resources with a link to the slides, link to other talks and tools and getting started stuff. So I hope you enjoyed the talk, and I'll be hanging around somewhere to talk to interested people afterwards. So thanks very much for having me, and hope to meet some of you soon.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.